Good morning and welcome to one more video. See, today I'm going to talk about the Newton's law of cooling. Okay, and all right, so this is coffee. This is very hot, and you can see the hot vapors are coming out of it, and this is very hot. Now it's very cold in Delhi, right? And we enjoy taking coffee during this weather. And Newton, the Newton's law of cooling is all about at what speed do objects, which are hot as compared to the surrounding. So this coffee, is probably, I think, is at 60 degrees centigrade. And the temperature in Delhi right now is, I think, 10 degrees maybe. So there is, a difference between the temperature of the object, which is coffee, and the surrounding. Right? The surrounding temperature is called as ambient temperature. So when I say Delhi, so this classroom, is at 10 degrees centigrade, but the object is at, maybe 60 degrees. And the purpose of studying Newton's law is to find out the rate at which this coffee is losing heat or the temperature is going down as the time progresses. Okay? So you're studying reduction in temperature as the time progresses. So we're dealing with the rate of cooling, which is also like a rate at which the temperature falls. And let me just write some of the stuff. It's very hot, okay? And it's very hot coffee. So enjoy the winters. And so let's write the Newton's law. So Newton, the way he articulated was that the rate at which the temperature drops is given by K, and this is T minus T naught. So he said the rate at which, and then you can add a negative sign here, or you can add a negative sign here. This is the temperature of my coffee, okay? So this is my coffee, and then this is my, the room temperature, which is the ambient temperature. Ambient temperature, okay? So I said coffee is at 60 degrees, and it is, the room temperature is 10 degrees. Always remember that when we do physics, a lot of physics is done in kelvins. So always convert it in kelvins. And so this is 273 plus 60 is, and this is 10 plus 273 kelvins. And you can just calculate this and get your answer, So this is 370, all right, this is, 283 kelvins. And you can also add this is 13 and 333 kelvins. All right, so you have a sense, right? This is a coffee which is getting colder as the time is progressing. Now it's been around, I think, 1 or 2 minutes. So the temperature of the coffee has dropped, okay? And so broadly, the Newton's law of cooling deals with objects losing heat, and the rate at which the temperature of the bodies drop, is dependent on the temperature itself, So let's assume a situation. I am taking coffee right now, and I want to write what is the rate, and this is a constant of proportionality. This is not like Stefan's constant, okay? Just be very careful. This is very different for all the materials, okay? And this is different. So this is K right now is for the coffee, okay? So the coffee I'm enjoying now is what we are focusing on. And let's say this is, so when I started, having coffee, my temperature was 333, 283. So my rate was minus dt by dt, is equal to K, and I started with 333, which is my tea coffee, and this is minus 283, and what I get, if I subtract these two is, 50 and K, okay? So this is my equation number one. So the rate at which the temperature was dropping, is this much, So this is obviously, this is Kelvin, and it's dependent on time. So this is Kelvin per second, and so it is getting cold, right? So I'm easily able to drink it. Now, maybe 2 minutes elapse, 2 minutes go by, which means the time now is 120 seconds, So I want to find out after 120 seconds, what is the rate at which the coffee is. So let's say after 120 seconds, the temperature of the coffee, instead of 60 degrees has fallen, it's getting colder, is 40 degrees centigrade, okay? So I can convert this in Kelvin and write this as 273 plus 40 is equal to 313 Kelvin. And I write this, my new rate, this is the initial rate, and now this is the rate at time is equal to, so this was t is equal to 0, this is t is equal to 120 seconds. And what I'm going to do is write this as K, so my room temperature remains the same, 283, but my coffee temperature is 313 right now. So 313 minus 283 is what I get, and this is amounting to 30K. Now you can see the rate at which the coffee is losing temperature has reduced. Okay, so this is a very high rate at which the coffee is losing temperature, and this is a lower rate. So if the temperature difference between the surrounding and the coffee is big, the rate at which the temperature drops is big. Okay, so this is bigger rate, right? K50 is bigger than this. Here the temperature difference was only 40 degrees, and here the temperature difference was like 50 degrees or 50 Kelvin, right? So it's very important to understand Newton's law, that the rate at which you lose temperature through the time as the time progresses is dependent on the difference between the temperature of the body and the ambient temperature, which is the temperature of this room, which I said is 10 degrees, right? So you can expect some numericals on Newton's law of cooling in your entrance examination, in your school examination. If you're grade 11, if you're grade 11, physics student, you can expect, irrespective of kind of board you're into, you can expect this. Okay, so this is, for you the what do you call it as the Newton's law of cooling. Okay. And just to be clear on when to apply this, see, this is generally applied in situations when, the temperature difference between the environment, which is what we refer to as the environment having ambient temperature and the temperature of the body, something like hot coffee, is not very large. So this delta T should not be very large, okay? But if the temperature difference is very large between the two bodies, for example, it's sun and earth, and we want to find out the rate at which, energy is getting, coming out of it, or the rate at which the sun is cooling down. In those circumstances, it is advisable to apply Stefan's law. Do not apply, Newton's law of cooling to the situations where it's a sun, getting cooler by the day or by the second, because the temperature difference between the sun and the surrounding is very, very large. So go for Stefan's law. Otherwise, tend to go for Newton's law of cooling in the situations where you have very limited temperature difference. And in a lot of situations, it's probably going to happen that the numerical is going to say, the Newton's law of cooling is pretty much applicable. I hope, some, So this is, if you go through your, physics class 11th, you find transmission of heat. And one of the chapters in transmission of, or the topics in transmission of heat is the topic of, the transmission of heat through conduction, convection, and radiation, okay? And under the concept of radiation, you study the multiple laws, all very important for the purpose of your entrance examination and for your day-to-day knowledge, So one of the important laws that we studied today was Newton's law of cooling. I'll just summarize it for you. It deals with the rate at which the body loses temperature. And it says that the rate at which the body loses temperature is dependent on the difference between the temperature of the body and the temperature of the surrounding, and hence the word delta T. K is not a universal constant, but is dependent on the type of material you use. So I hope you enjoyed this video. I conduct live classes. You're very welcome to join them, and you can send me a WhatsApp on the number given in this video for further details. Have a good day. Thank you very much, and enjoy your coffee.